Okay, good morning, everyone. So today we will still continuing our discussion about fluid flow. And in our last discussion, we have discussed about the Bernoulli equation. So basically, Bernoulli equation is the equation that represent energy balance in fluid flow. So basically, when fluid is flowing, you will have these four types of energy, which is the internal, kinetic, potential, and pressure energy. It has their own formula, yeah, how you calculate the value of the energy for each component, and certain parameters. Each energy is influenced by different parameters, and especially for energy in Bernoulli equation, Bernoulli equation is basically the most simplified terms of the energy balance. Yeah, this is the component of the Bernoulli. The assumption would be the flow is very ideal. It means there is no energy loss, so the flow can be considered isothermal. So you will not have this internal the change of internal energy for Bernoulli equation. Yeah, in Bernoulli equation, then it's only comprised of three types of energy, which are pressure energy, and then potential energy, and kinetic energy. So this is the general term. So if you write in terms of energy, so this one, right? Let me. Yeah. So this is the component of energy in Bernoulli. So if you write the Bernoulli equation in terms of energy, so it would be this one. This is the pressure energy. Pressure energy is pressure times volume. So pressure times mass divided by the density. Yeah. And then for the potential energy, this one, H or Z, is don't get confused with the symbol. And then this one. The total should be constant. Yeah, this is the term in energy. The unit will be joule. You can divide all the component divided by the mass, so you get this formula. If you divided all the energy component by the mass, it becomes specific energy. Yeah, becomes specific energy. And then you can divide it again with the gravitational energy. So it becomes like this. If you divide it again by the gravitational energy, it will become head. Yeah, like this one. The unit will be length or height. Yeah, but it's still all are energy. Just difference in how you state the unit. It can be in terms of energy, joules, in terms of specific energy, joules per kilogram, or in terms head, in meters. In the video that we have watched previously, then you can use in terms of pressure. So for this one, you can like this, yeah, multiply by the density. So each component will still be energy, but the unit is pressure. So the pressure unit, if you are using standard unit, it will be Pascal. All component, even though it's pressure energy, kinetic energy, or potential energy, the unit is still it's still energy, but the unit become Pascal. Jadi jangan bingung ya. Jadi energinya bisa dinyatakan dalam bentuk, tidak hanya dalam bentuk joule. It's not only in joules. it can be in other unit. Especially we use head unit. Yeah, head unit is commonly used as well. I think in our last discussion we have I have shown you how to represent the energy in terms of head. Yeah, at this point, with this figure, you express you analyze using the Bernoulli equation between point 1 and point 2. Point 1 will be atmospheric, right? And then at point 1, because it's atmospheric, please remember again that if you express the value of the energy, it can be you can compare it with the baseline of the same energy. Like if you want to express the pressure energy comes from the pressure, right? So the baseline value for pressure, you can use the atmospheric pressure. So in terms or with the baseline of atmospheric pressure, then at P1 will be equals 0 relative to the atmospheric pressure. Yeah. And since the tank is quite big, it's very, very big, I mean, so there will be no movement in the tank. So the velocity, sorry, this one equals 0. Okay. So in point 1, energy is only from the static energy, or we call it static head. So from this one only, so head is only from Z1. Total head at point 1 is only from Z1. How about at point 2? At point 2, there will be a movement, right, in point 2, because in the slanted pipeline, the water will be flowing, and then at point 2, there will be some value of velocity. So you have the value of the velocity, and then how about the static? It means you have velocity head. How about the static head? The static head can be measured from the baseline. Baseline is here, and then the static head will be this one, where Z2 will be lower from Z1. Okay, so you will have decrease in static head, but you will have, because velocity at point 1 equals 0, and at velocity, so do like this, right? The velocity at point 2, you have the it will have the value of the velocity. So velocity at point 2 will be larger at point 1. It means some of the energy can be converted to other types. The static energy is decreasing. The velocity energy is increasing. So it will be some increasing of pressure energy. Ya. Jadi karena energi statiknya itu turun, energi kecepatannya naik, kemudian energi tekanannya juga akan naik. So this will be representing the pressure head, the pressure energy, and this will be this one representing the velocity head. Because basically at point 2, pressure at point 2 will be the pressure at point here at point 3. Pressure at point 3 will be the atmospheric pressure, right? So relative to the atmospheric pressure, you can say that this one, relative to the atmospheric pressure. And pressure at point 2 will be the density times H times G times H. H is the head difference. So this part is static head, this part is pressure head. So the remaining one is the velocity head. Okay. The total should be the same as this one. And you can see the head is the same, right? So this is the total head of point 2. The same as the total of point 1. Okay, any question about what we have discussed previously? Suara masih terdengar ya? Takutnya mati lagi.
We can still hear you, sir.
Okay. Okay, any question about this system? How to explain the Bernoulli in terms of the head? So you can understand better why we can express energy in height or length unit. Okay, if you have no question, then I will ask you. If we move the point 2 lower, yeah, I mean the point 2, let's say it's point 2, this is point 3, and then you move point 2, let's say at point 4. What will be can you guess what will happen with the head of the water at point 3? Will the head be increasing, decreasing, or constant? Ya, jadi kalau titik 2-nya Anda geser ke bawah ya, ke titik 4 katakanlah. Ujung manometer yang kanan dipindah ke 4 ya. You shift the right leg of the manometer from point 2 to point 4, and then you observe the head of the water. Will the new head of the water will be lower from point 3 or higher or constant? Anyone would like to answer?
Constant, sir.
Constant. Why?
Because the lower you go, I guess the potential energy decreases. Thus, it has to convert to some other energy. So it should be the pressure.
Okay.
Right? So if 3 is constant and 4, if 3 is constant compared to the previous spot, the pressure difference will be higher.
Okay, why it not goes higher or lower? You means the pressure will be higher, right? If you shift the point 2 to point 4, the pressure head will be higher. But
Yes.
why the position of point 3 is still the same? It's not go ups or go down. Yeah, can you explain? Your answer is correct. Your answer is correct. The pressure head will be higher because the static head is lower. But my question is why the position at point 3 is not go up? Because the pressure head is higher, right? Kenapa posisi titik 3-nya itu tetap di situ? Kalau geser ke titik 4, posisi 2 geser ke 4, kenapa posisi titik 3 tetap di situ?
Because the velocity head will be constant.
Yeah, the velocity head will be constant. Why the velocity head is constant? Because the water are traveling through the same diameters of the pipe. Yeah, the diameter of the pipe is the same. The volumetric flow rate is the same, right? The mass flow rate is constant. If the density is constant, then the volumetric flow rate is also constant. So if the pipe cross area is constant, then the velocity is also constant. If the velocity constant means the velocity head will always this much. So the increasing in pressure energy or increasing in pressure head is just the difference, the new difference from point 3 to point 4. The length is longer, right? It means the pressure head is also higher. Okay. I hope you can understand. Or do you have any question? Yeah,
I do have a question, sir.
Yeah, sure.
So wait, So why does the velocity head decrease the height of the liquid of from point 1 to point 3?
Sorry.
So that velocity head, right? It is I guess the height between 1 and 3, right, sir? Yeah, I don't see how that decreases it, or why is there like why is the velocity head corresponding with that difference in height?
Okay. Why this line is representing the velocity head, you mean?
Yes, sir.
Okay, yeah, because this line representing the static head, and then this line representing the pressure head, while the total will be this length. Jadi dibalik ya, karena ini adalah static head, because this is the static head, this is the pressure head. By the definition, you can understand, right, why this height difference represent the pressure head of the point 2. The pressure head is actually, the pressure at point 2 is actually atmospheric pressure plus rho g times height difference, this time times this height difference, right? So this is the pressure head of point 2. If you have the total head is this much, yeah, from 0 to Z1, then the rest will be the velocity head.
Okay, sir. I understand.
Yeah. So this is the last one that we need to calculate. Okay, any other question? Okay, if you have no question, then I will go to the next slide. So this is the application of Bernoulli, yeah. We call it tank emptying, or in Indonesian you can say tangki bocor, yeah. You have a quite big tank, yeah, containing water, and then the diameter of the cylinder, the tank is D1 at position 1, yeah, and then yeah, so you have D1 at position 1, and then at the bottom of the tank you have very small hole with the diameter of D2. What happens when you have holes in the at the bottom of the tank? Water will flows out, right? However, for this case, we can assume, since the tank is very big, even though you have water flowing out from the tank, the head at point 1 is remaining constant, so it's not goes down. It means at point 1 you can assume the velocity is 0. Velocity at point 1 is 0. Okay, how about the pressure at point 1? What is the value of the pressure at point 1? It's open to the air, so the value will be tekanan detik 1 berapa kalau itu terbuka ke udara?
Atmospheric pressure.
Yeah, it's atmospheric pressure. Yeah, atmospheric pressure. Okay, if at point 2, so P1 will be atmospheric pressure. At point 2, water flows out, and at point 2, it's also open to the atmosphere. Yeah, so it's open to the air. It means at point 2, the pressure will also atmospheric, because you have hole at point 2 and water comes out, so the pressure is also atmospheric. If there is no hole at point 2, what will be the pressure? Kalau di bagian 2 itu tidak bolong, ya, airnya tidak mengalir keluar, apakah P2 sama dengan P atmospheric? If there is no hole?
No, sir.
Okay, so how much is the pressure at point 2 if it is not atmospheric?
Density times gravity times height.
Yeah, it should be atmospheric plus, don't forget this one, yeah, the density of the water times gravity times the height. Yeah, it applies when the bottom of the tank is closed. It's not open to atmosphere. But for now, the condition is open to atmosphere, and water flows out. Okay, sampai di sini. Until this point, you have any question? Okay, then by analyzing using the Bernoulli, you can make at point 1, P1, this one, Z1, yeah, this is the total energy at point 1 will be equal to this one. Okay, P1 and P2 is the same atmospheric pressure, so you can cancel it out. And then, since the baseline is 0.2, so Z2 equals 0. Okay, since at point 1 there is no movement of the water, so this one equals 0. So by using the Bernoulli principle, you can calculate the water velocity at point 2. How much water will be flowing out through the hole by using the correlation of the Bernoulli, and then from Z2 to from Z2 to Z1, it will be H, right? So you can get this one. Ya, dari hubungan ini. And then this is velocity, meter per second. So if you know in terms of flow rate, cubic meters per second, flow rate will be velocity times cross area. So this will be A at 0.2 times the velocity. Okay, hope it's clear enough, or do you have any question? Okay, then I continue to the next part. This is the schematic diagram of diffuser. Diffuser is one type of pipe fitting. Fitting is pipe accessories, please remember. Yeah, so the function of diffuser is you want to connect smaller diameter of the pipe to bigger diameter. So you are using the diffuser. Okay. By analyzing this schematic diagram of the diffuser, you have point 1. Point 1 is the inlet, and point 2 is the outlet. Then you can derive the mass balance. Yeah, mass balance, mass flow rate at point 1 is equals to point 2. Mass will be density times velocity times area. Since we can assume the density is constant, yeah, the density, you can assume it is constant, then you can have the correlation between velocity and the diameter ratio. Yeah, by analyzing uses the mass balance equation, you have the correlation between velocity and diameter ratio, and then you can conclude that in diffuser, because you have larger diameter at the outlet, yeah, this one, then the velocity will be lower. Okay. Yeah, this is based on the mass flow rate. Okay, after deriving the mass flow rate, after deriving the mass balance equation, the continuity equation, then you can derive the Bernoulli equation. by comparing the total energy at point 1 and total energy at point 2. Okay, first we see the static energy. The baseline for this schematic diagram of diffuser is this one. So this is the center of the diffuser. It means Z1 will be equals Z2. Yeah. So the Bernoulli equation is only comprised of pressure and velocity. Then you can derive further to see the correlation between the difference of the pressure at point 1 and point 2 in terms of velocity. You have correlation between pressure and velocity. Since at point 2 you have lower velocity, then you have higher pressure. You can imagine, right? Bernoulli, the static energy is constant because the heat is constant, yeah. And the kinetic energy is higher, yeah, at the outlet. At the outlet, the kinetic energy is higher because the velocity is higher. It means the pressure energy become lower. The pressure become lower at the outlet. Okay, please do not menghafal mati ya. What can I say in English? Please do not just memorize the final equation, but please try at home at your own convenience to derive all the mass balance and then derive all the Bernoulli equation and then try to derive the correlation between pressure difference and velocity. Okay, to ask you, and then this is based on the Bernoulli. Bernoulli assume ideal flow. Yeah, Bernoulli assume ideal flow. It means in the flow there is no energy loss. Ya, jadi kondisi ideal ya, Bernoulli itu kondisi ideal. Dalam kondisi ideal diasumsikan tidak ada energi yang hilang. The energy is only transferred to one form to another between these three types of energy. Okay, my question is if you have energy loss, what kind of energy loss that you might have during the water flow or the fluid flow? Lydia, are you there?
Yes, sir.
Yeah. If you have energy loss, Bernoulli firstly assume there is no energy loss. But in real condition, you will have loss of energy. Can you guess what types of energy loss that might be encountered in this situation?
Maybe friction, sir.
Friction. Okay, friction between?
The liquid and the fluid and the pipe.
Yeah, between the layers of the liquid and between the water and the pipe wall. Correct. And then the energy loss will be in terms of heat. Yeah, it will be lost to the environment in terms of heat. Okay, if you have energy loss, what will be the effect to the pressure or to the velocity at the outlet? Can somebody else try to answer? Ya, kalau ada energi yang hilang ya, tadi sebagai friksi, energinya hilang sebagai panas ke lingkungan, efeknya apa? Terhadap kecepatan keluaran atau terhadap tekanan keluaran?
I guess the velocity will decrease.
I'm sorry, I cannot hear you clearly. I think you have some disturbance in the sound.
Maybe the velocity will be decreasing, sir.
The outlet velocity will be decreasing compared to ideal. Is that what you mean?
Yes, sir. Yes,
Okay.
sir.
Can you explain why? Why the velocity at point 2 when you have real condition with friction, the velocity at point 2 is lower than in ideal condition?
I guess because due to friction, there will be like loss of energy. So maybe the kinetic energy will go down. So the velocity will also go down, I guess, sir.
Okay, yeah, that's correct. So if you want to analyze the effect on the velocity, then you must assume first there is no change in the, I mean, not change in the pressure, but the loss of energy is compensated in the velocity only. Yeah, it means if we compare ideal, Bernoulli, ideal is the Bernoulli, vs non-ideal. Yeah, we have this one, right? Yeah, the velocity is decreased. I mean, compared to the inlet. Yeah, if you compare inlet to outlet, the velocity will decrease and the pressure will increase. Yeah, so if you define delta P as pressure difference, yeah, so if you assume from ideal to non-ideal, delta P is constant. Yeah, delta P is constant. It means it will be compensated to the velocity. Yeah, then the velocity will be lower. Correct. U2 in non-ideal will be lower than U2 in ideal. Okay. In terms of velocity is correct. How about in terms of pressure? In terms of pressure, if you assume U2 non-ideal is the same as U2 in ideal, yeah, velocity of outlet velocity in ideal condition is the same as outlet velocity in ideal condition. Yeah, between non-ideal and ideal is the same. What will be the effect of the pressure at point 2? If you compare pressure at point 2 in non-ideal condition and ideal condition. Gimana? Anyone try to guess the answer? Raihul, Muhammad Raihul, are you there?
Yes, sir.
Yeah. Care to elaborate the answer?
I'm sorry, sir. Would you mind repeating the question? Your voice back then was so low.
Oh, is it? Just a sec. How about now? Is it clear already?
Yeah, it's a bit better now. I already maxed out my volume, but it's still low. But I can still hear it.
Okay, I don't know what happened actually with the sound of my Zoom. Okay, previously we have discussed the effect on the outlet velocity. Yeah, for the outlet velocity in non-ideal, in the real condition, it will be lower than the ideal outlet velocity if you assume constant pressure difference. Now we flip the condition. So the outlet velocity remaining constant in real condition, it means the energy loss is compensated to the pressure energy. So what will be the outlet pressure? In non-ideal, in real condition, what will be the outlet pressure compared to the outlet pressure in ideal? Will it be lower or will it be higher?
I'm guessing it will be higher than A.
Right?
It will be lower than the ideal.
Why?
I'm just basically
Just guessing. Okay. Anyone else? Do you have any opinion?
Sir, is it lower? Or
Yeah,
because in the non-ideal, it's losing some things, yes, like the heat. So it will compensate with losing pressure as well.
Okay, yeah. So if we assume the velocity at point 2 is constant, yeah, not constant, it's the same between the ideal and non-ideal, it means the amount of energy, the change from the kinetic energy, some part is lost to the environment, right? So the amount that's compensated into the pressure energy will be lower. That's why P2 will be lower. Yeah, in real condition. It means delta P in non-ideal will be lower with delta P in ideal. I hope you are not confused with explanation. Just try to use your imagination and logic to analyze this case. So we are comparing between the real condition when there is where there is energy loss compared with the ideal from the Bernoulli. So both in terms of velocity, it will be lower, yeah, if you assume pressure difference is constant. But if you assume velocity is not changed, then delta P, pressure difference, will be lower. Okay, do you have any question? Okay, then I'll move to the second one. This one is the opposite diagram of the diffuser. We call it reducer. So the reducer connecting from bigger diameter to smaller diameter of the pipe. Basically, if you analyze from point 1 and point 2 using mass balance, yeah, using mass balance and then using Bernoulli equation, the equation will be exactly the same. Ya, kalau Anda menggunakan neraca massa dan neraca Bernoulli, itu bentuk persamaannya akan sama persis, exactly the same. However, the difference, because you have A2 is smaller than A1, then U2 will be, U2 will be higher, right? So for the diffuser, U2 will be higher because the area is smaller. How about the pressure? If the velocity is increasing, then the pressure will be higher or lower at the outlet. Hello? Okay, I think I have to ask Alika, Zahra.
Yes, sir.
Yeah. So pressure at point 2 compared to point 1, is it higher or lower?
I think the pressure in point 1 will be higher than P2.
Yeah. Or P2 is lower.
Lower.
All right. Okay. Now we discuss again about ideal and non-ideal condition. Yeah, by defining pressure difference is this one. Or because P1 is, sorry, let me change this one. So we will have a bit different definition of pressure difference, yeah, because P1 is higher than P2, then you can write down this one. Okay, now we use the same approach. If in non-ideal condition, non-ideal, when there is energy loss, delta P is the same between non-ideal and ideal. How about pressure? How about the velocity in point 1, in point 2 compared to ideal? If you have energy loss, but you have constant pressure difference, yeah, the velocity at point 2 will be higher or lower in real condition, in non-ideal condition. Cherry, Gracia, are you there?
Yes, sir.
Yeah, okay. Can you try to answer?
I guess lower.
Why lower?
I'm not quite sure. I'm just guessing.
Why are you just guessing? You can try to do the same logic or to do the same analysis as the previous case. Please try to explain. So you have a certain amount of energy, yeah, the total amount of energy at point 1. It comprised of the static energy, the kinetic energy, and then the pressure energy. Okay. At point 2, because the level is the same, yeah, the baseline is this point, is this line, so there is no change in static energy. So it's only between the kinetic, the velocity, and the pressure. And point 2, you have higher velocity compared to point 1. Yeah, we compare outlet to inlet. You have higher velocity. It means the kinetic energy is increased. So you will have decrease in pressure. Yeah, and the change of pressure between inlet and outlet you express at delta P. Okay. Now we go to the non-ideal case. In non-ideal case, the amount of energy in point 1, at point 1, some of the amount is lost to the environment. It means the one that should be transferred to point 2 will be lower, right? In real condition. So if the total amount of energy transferred to point 2 is lower in real condition, but the pressure difference is the same, it means the velocity will be lower, right? Cherry, are you still there?
Yes.
Are you asleep already?
No. I'm just
okay. Yeah, you can
to...
understand, right? Because it's lower because the amount of energy that should be converted to the velocity energy or the kinetic energy is lower in real condition. Okay. This for the case of the same or constant delta P. Now we use the approach if Z2 non-ideal is the same at, U2 non-ideal is the same as U2 in ideal. How about P2 non-ideal compared to P2 ideal? Lower or higher? Let's go up. Kanzu, are you there? I think I have asked you many times. You never answer.
Yes, sir. I'm no. Did I?
Yes.
Did you, sir?
Yeah. Can you
I think
answer?
I've answered. No, I mean, I think if you call me, I always answer.
Yeah. So for this case, pressure at point 2 in non-ideal in real condition Is it lower or higher than in ideal condition?
Pressure in point 2, I believe it is lower, if I have to guess.
Okay, your guess is correct. And basically, it's the same reason with the case of the velocity, because you have less energy compared to the ideal condition. So the pressure at point 2, the real one, will be lower. So if P2 is lower, then delta P will increase, right? The pressure
Yes, sir.
difference or the pressure drop will be increased. Okay. Any question? Hopefully you can follow the explanation. Okay, if you have no question, then I should continue. Okay, this is another type of fitting. We call it sudden enlargement. Basically, why it's called sudden? Because it has sudden change of diameters. Yeah, the arrangement is at the left one, at point 1, the diameter will be smaller than diameter at point 2. Yeah, inlet is smaller than outlet. If you just compare point 1 and point 2, it's the same with diffuser. Yeah, the inlet diameter is smaller than outlet. However, in sudden enlargement, you will have sudden change of the diameter. So if you take the baseline at the center, yeah, the same, right? C1 equals C2, then basically you will have exactly the same phenomena as diffuser. Because at point 1, because you only observe at point 1 and at point 2. You just compare 2 points. Okay? So how you derive the mass balance equation, the continuity equation, and how you derive the Bernoulli equation, it's all the same. You will have the same correlation, you will have the same final equation, and you have the same this one. Yeah, the velocity is decreasing at point 2, and the pressure is increased. Then you can calculate the correlation between the velocity at the outlet and the pressure difference. Okay. Now I want you to guess again. In terms of energy loss, which one is higher? Sudden enlargement or diffuser? In terms of energy loss. Or in terms of pressure drop, yeah, pressure drop or pressure difference. If you have energy loss, yeah, which one will be higher, and why? Diffuser or sudden enlargement?
Is it sudden enlargement, sir?
Why?
Because the change of the cross section area is big, like the surface area. I don't know. That's my guess, sir.
Okay. For example, if D1 diffuser the same as D1 sudden enlargement, and D2 of diffuser is also the same as D2 of sudden enlargement. Okay. Ukurannya sama, diameter masuk dan keluarnya sama. Hanya bedanya yang satu gradual ya, the change is gradual, and the other one the change is sudden. Okay, which one will give higher energy loss? Which subsequently give higher pressure difference?
Oh.
Diffuser or sudden enlargement?
I feel like sudden enlargement, sir, still.
Okay, and the reason?
Yeah, because it's gradual. It's like in sudden, it's suddenly, like suddenly boom. You know what I mean? Sir? It's big, so like it fills the area faster, so the energy is needed more. I mean.
Okay. Yeah, okay, I got what you mean. So basically, if you have water flowing from smaller diameter and then suddenly change to higher, bigger diameter, there will be like turbulence in this area. Yeah,
Yes,
the one
that's
that
what I meant.
yeah, the one that you say boom, it means the turbulence in this area, and that's correct. The change, the sudden change of the diameter will provide higher energy loss, will gives bigger energy loss because there is change in flow pattern of the liquid. Yeah, compared to the diffuser. The diffuser, the change is gradual, right? So the water just flows smoothly, but it still it will still have energy loss because of the friction. In this sudden enlargement, you still have friction, so you still have energy loss, but you have more energy loss due to the turbulence of the water around the enlargement area. Okay, basically, this equation is derived from Bernoulli, correlation between velocity and pressure difference. Okay, if in not if in real condition, when you have friction, you have turbulence, you have a change of flow patterns, you need to incorporate what we call the correction factor or correction, or we call it fitting constant. Yeah, basically fitting constant correlate the velocity and the pressure difference. If you have very ideal flow following the Bernoulli, which is not going to happen in the real case, the correct square root of pressure difference. Okay, but in real condition, it will still, okay, in real condition, it will still following the Bernoulli, but you need to incorporate the correction factor, so it's still proportionally correlated, but it will be less than 1. I mean the comparison, the ratio between this one and this one. Ya, jadi ada faktor koreksi when you correlate between the velocity and pressure difference, the square root of pressure difference, there will be, in real calculation, there will be the correction factor or the fitting constant. Okay, then my question, how to get this correction factor? Do you have any idea? Dapatnya dari mana? Angka koreksi faktor koreksi ini dapatnya dari mana?
Compare the result from Bernoulli to experiment.
Yeah, you compare the result. You get the value from the experiment. How to do the experiment? Galang, do you have idea how to compare, how to get the data, right?
Using flow meters, sir?
Using flow meters, and then so you flow the water through the sudden enlargement. Okay, you have the data, right? You have the data of the ratio of the diameter, yeah, d1 over d2. You have the data of the water density. Then you flow the water, you calculate the flow rate of the water. You calculate the flow rate either at 0.1 or 0.2 using the flow meters, or if you do not have flow meters, you just do it manually, right? You contain the water to certain measurement glass or maybe a bucket, but in the bucket you have write down the the volume, like until this line is 1 liter, 2 liter, etc. And you take the time. You take notes of the time. So you get the flow rate, volume over time. Then you need to calculate the pressure difference. You need to get the value of the pressure difference. How to do it? Maybe you can install the manometers. Later I'll show you how to use the manometers. I think in the fluid static we also have explained about the manometers. Then you get the pressure difference. Then you just correlate. You variate the flow rate. You variate the flow rate. You get the pressure difference. Then you can take the data. It will have the straight line, and then you can get the constant. The gradient will be the constant. Kebayang ya? Later, if in the experiment in lab tech, you will try to have this type of calculation. Okay, any question?
Sir, I have a question.
Yeah.
So before you said that the sudden enlargement, there's energy loss, right?
Mm-hmm.
Like bigger than the diffuser.
Mm-hmm.
So I assume that not all the kinetic energy is converted into a pressure rise, right?
Yes, correct. Mm-hmm.
So where does the energy go? Like, so the first law of thermodynamics says like energy is conserved, right? So where does the remaining energy go if it's not converted to pressure?
So the energy loss will go to the environment, yeah, because of the friction. The turbulence actually adds up the friction, yeah. Later when we discuss about the friction loss or friction energy, the turbulence also contribute to the friction, and energy will be lost in terms of heat, ya, to the environment. Jadi ada energi yang dilepas sebagai panas ke lingkungan. However, this maybe the energy loss in terms of heat, if you measure using the thermometers or other types of temperature measurement, then actually the value is not that big. But I mean the temperature difference is not that big. However, there's still substantial amount of energy loss because the pipe arrangement it's never just short pipe, right? It will be a very long pipe. Maybe can reach up to certain kilometers. Ya, jadi kalau jadi hilangnya energi friksi itu menjadi energi panas. The loss will be into the heat loss. But if you think about heat, it will be correlated with temperature, right? So if you measure the temperature difference, there will be no significant amount of temperature difference. If you touch the surface of the wall, for example, of the pipe, the outer wall of the pipe, you cannot feel the temperature is increasing. However, it's still there is some heat released to the environment. And since the pipe arrangement is quite long, yeah, reach certain kilometers, then the heat loss or the energy loss is substantial. That's why the pressure drop or the pressure drops will be much higher than the ideal one, and the velocity will be much lower than the actual one. Okay, I hope it answered your question.
Yes, sir. Thank you.
Okay. Any other question? Okay. The other types is sudden contraction. Sudden contraction is the opposite of sudden enlargement, and the basic schematic will be similar to reducer, from bigger diameter to smaller diameters. So the phenomena is the same as the diffuser, as the reducer, when the Z1 is the same as Z2, right? Because it's always at the middle of the pipe. And then A2 is smaller than A1, so the velocity at point 2 is higher than point 1, and the pressure at point 2 is lower than point 1. Same with reducer. Okay, however, this sudden contraction will contribute to more heat loss, more energy loss in real condition. So if you compare sudden contraction and reducer, or sudden enlargement and diffuser in ideal condition, it's exactly the same. Yeah, the amount of energy transferred, if the dimension of the diameter is the same, the diameter ratio is the same, the amount of energy that can be transferred from point 1 to point 2 between the sudden contraction and reducer, or between the sudden enlargement and diffuser in ideal condition is exactly the same, because there is no energy loss. But in real condition, with energy loss, the sudden one will give more energy loss, more friction loss due to change of the pattern. This is the same. It will have like turbulence around the contraction area. So it will be contributed to the lower velocity or higher pressure drop compared to the ideal. How to derive the equation? It's exactly the same. You will have the correction factor as well. But if the correction factor equals 1, it means ideal. The equation from the sudden contraction will be the same as reducer. Okay, I suggest you to take some practice to derive the equation, yeah, from the mass balance equation, and then combine with the Bernoulli equation for each type of the case. Then you can try to analyze. It should generate the similar equation. Okay. Okay, now I'll continue to the next part. Okay, the principle of Bernoulli or the Bernoulli equation basically can be used as the Bernoulli equation, the principal one, can be used in the fluid flow rate measurement device. By the name, the measurement device is to measure the flow rate of the fluid. Okay, first is the pipette tube. Yeah, the pipette tube. The picture is like on the left figure. So it's normally placed in the plane or in the ship with the tip. This is the tip of the pipette tube. It will face to the direction of the plane. Yeah, so it will measure the velocity of the air with the direction opposite to the plane's direction. Ya, jadi ini pitot tube-nya ini biasanya dipasang di pesawat atau di kapal gitu ya. Moncongnya ini menghadap ke arah depan pesawat. Dia mengukur kecepatan pesawat dengan cara mengukur kecepatan udara yang arahnya berlawanan arah ya dengan gerakan arah pesawat. Ya, the tip basically it measures the velocity of the fluid. In this one, this is the velocity of the air, but the direction of the air will be opposite to the direction of the plane. And the velocity of the air measured will be the same as the velocity of the plane. Okay, this is the schematic diagram of the pipette tube and how pipette tube can measure the velocity of the air. Yeah. Point 1 is it is at the location of free air flowing. Yeah. So it represents the velocity of the air and represent the velocity of the plane. This is point 1. And then point 2 is at the point when the air is flowing to the pipette tube, and then it will in contact with the manometer inside, the manometers will have certain types of the fluid. So it will pressurize, yeah, it will pressurize the manometer fluid until certain position. Then the leg of the manometer will provide certain height difference. After it provides certain height difference, the manometer fluid will remain constant at this position. Okay, if the manometer fluid remains constant at this position, what will happen with the air inside the pipette tube? Halo? Karunia bintang.
Yes, sir.
Yeah.
Sorry,
What will
could
happen
you-
with the air
Okay.
inside the pipette tube?
Could you repeat the question, sir? I couldn't hear you clearly before.
Yeah, the question is what happened with the air inside the pipette tube? If it's pressurized the manometer fluid, and then the manometer, first you have air, right? Air flowing freely, yeah? And then some of the air will flows into the pipette tube until, and the air in the pipette tube will pressurize the manometer fluid. So the gray area represent the fluid inside the manometer, yeah, until certain time. Then this manometer fluid will shows this position, so it's constant in this position. Okay, if the manometer fluid is constant in this position, what will happen with the air inside the pipette tube? Hello, are you still there?
Yes, sir. I'm not quite sure. Would it be constant, sir?
Yeah, the air in the pipette tube will be static, right? It will not flowing anymore. Paham ya? Can be understood? Yeah. First, it will flows. The air will flows, pressurize the fluid manometers, and then fluid manometers will be static. So the air will also be static. It means at point 2, velocity at point 2 becomes 0. Yeah, this one, 0.1. This is the velocity of the air. And this is the velocity of the plane that we want to measure. At point 2, the velocity is 0. Because point 1 and point 2 is at the same height, so Z1 equals Z2. Okay, then you can apply the Bernoulli equation. I need to make some, because the Bernoulli equation will be like this, right? Will equals to this one. Okay. Z1 and Z2 cancel out each other because the position is the same. And then at point 2, the velocity is 0. So you just have the correlation between pressure and velocity at point 1. Velocity at point 1 is the velocity of the air, is the velocity of the plane. Okay, then how you can get the value? So you can get the value of velocity at point 1 by measuring the pressure difference. This one. Then how you can get the pressure difference between P1 and P2? P1 and P2, which one is higher?
P2, sir?
Yes, it's P2 because the velocity at point 2 is already 0. So the velocity is decreasing. It means the pressure is increasing. Okay, so the difference between P2 and P1, can you get the value or can you obtain the value of the pressure difference?
Rho G delta H.
Rho of what?
Of the liquid with the lines.
Yeah, this one. Yeah. So if it's PA, this is the density of the manometer fluid times G times delta H. Yeah. So please pay attention. In calculating the pressure difference, you need the value of manometer fluid's density. But in Bernoulli equation, you will have this one, right? You will have this one. This is the air density. Don't be mixed up, jangan kebalik-balik ya. Jadi ketika di Bernoulli, ada persamaan ini ya, persamaan Bernoulli, you have rho. Rho is density. This is the density of air. But when you want to calculate the pressure difference can be calculated, can be correlated with the head difference of the fluid manometer, the manometer fluid. So you need to use the value of the manometer fluid, the manometer fluid density. Okay. Do you have any question? What is CP? CP is basically the same. This is the correction factor from ideal Bernoulli to the real condition. Okay. The other one, the other flow measurement device is the orifice. Orifice is basically if you have a pipe, yeah, you install a plate inside the pipe that have very small openings, very small holes, like this one. What will happen if you have very small holes? Then this is point 1. Point 1, for example, you have water flowing to the pipe, yeah. You have the you want to measure the water's flow rate or water's velocity, this one. So in order to measure this velocity, you install the orifice, and then what happened with the velocity at point 2? If you have small diameters, how if you compare velocity at point 2 and velocity at point 1, it will become higher or lower? The velocity.
Will it become lower, sir?
Why lower? The velocity. If you have smaller diameters, smaller cross-sectional area, then the velocity will decrease or increase?
Increase, sir.
Increase, yeah?
Increase, yes.
Correct, yeah, because A2 is lower. So if a velocity at point 2 is higher, then the pressure will increase or decrease? Azra, still Azra. Hello?
Yes, sir. I'm thinking. If
So if U1 equals Z2, so it's only between the kinetic and pressure, right? Because the static is constant. So if the velocity is increased, the kinetic is increased, then the pressure?
The pressure will decrease.
Decrease, yes. Okay, yeah. So the pressure is decreased. It means you have different pressure between point 1 and point 2. Then how to calculate the pressure difference? Actually the same. You can install the manometers. The leg of the manometers should be connected to each point where there is pressure difference. Ya, jadi kakinya manometer itu harus dipasang pada posisi di mana dua titik tadi punya beda tekan. Ya, you need to install the manometer legs at two position where there is a pressure difference. If you put the other leg, yeah, like one leg is here and one other is here, what will happen? What will be the velocity at this point compared to this point? Brian Nimrod, Budiman Sianturi.
Yes, sir.
Yep. What is the value of the velocity at this point compared to the point 1? It's like further away from the orifice. What will be the velocity?
The
is it
velocity
higher? Is it lower or the same?
If I have to imagine, sir, and guess, I would think it would be lower because there is an obstruction.
It's much further after the orifice. So the orifice is like this one. The water flowing, right? Like you install the orifice and then it's flowing again, like it's further from the orifice. So the velocity here compared to point 1?
Oh, so it's further away. I suppose it's the same.
Yeah, it is the same.
Oh.
Sudah jauh dari orifice ya, because it's already further away from the orifice. The velocity backs to velocity at point 1. So if you install at this point compared to point 1, there won't be any pressure difference because the velocity is the same. So the pressure will be the same and there is no pressure difference. Ya. Jadi kalau dipasang jauh setelah orifice ya, yang satu mungkin di depan, yang satu di belakang tapi jauh, itu nanti nggak akan ada beda tekanan. Karena kecepatannya sudah balik lagi kecepatan di titik 1. Kalau kecepatannya sama, tekanannya ya pasti sama ya, tidak ada beda tekan. With assumption there is no energy loss, of course. Hanya 3 komponen tadi ya, tapi kan statiknya tetap. Jadi tekanannya sama, kalau dipasang di sini nggak akan ada beda tekan. If there is no pressure difference, then there is no height difference in manometers. So you need to install one leg of the manometers to the position just after the orifice, since you need to have pressure difference. So like this one, which leg is higher? If you have manometer fluid, yeah, which one have higher height? At left leg or right leg? If you have higher pressure at point 1 compared to point 2, yeah, pressure at point 2 is lower than point 1. So the height of the manometer fluid will be higher at point 2 or point 1.
I suppose point 1, sir.
Why? So the position is like this. If you have, for example, mercury inside the manometers, so the position is like this. the pressure at point 1 is higher. If you have higher pressure at point 1, what will be the difference between manometer slack? This one or this one? Brian, still Brian.
If the pressure in point 1, yes, sir, is higher.
The pressure at point 1 is higher.
Well, I suppose this one is correct, sir, because it pushes the mercury towards point 2.
Yes, correct. Yeah, because it will push away the mercury to the left, to the right side. So there will be heat difference, and at point 2 the heat will be higher. Paham ya? Yang lain bisa dipahami ya. Jadi so you need to install the manometers with different types of fluid, yeah, because you want to measure the velocity of the water. Then by installing the orifice, you have a pressure difference. The pressure difference is measured by the heat difference of the mercury. Then you can get this one. The equation is the same. Just try to rewrite the equation. Beta is basically the diameter ratio, yeah, this one. The smaller diameter over the bigger diameter. So try to derive. This is the volumetric flow rate. This is the velocity. Not volume, yeah? This is the velocity. So try to use the mass balance and then try to derive the Bernoulli equation. Then you will get the correlation between this one. Okay, this one, the pressure difference is basically the heat difference. You need to know the value of manometer fluid. This one is the value of the water. This one, the fluid that's flowing inside. Okay, any question?
Sir, I have a question. Will the water experience any turbulence after crossing the small hole later? Or no?
Yes, it will. Yeah. So in real condition, it will create turbulence. So basically, there will be pressure. There will be energy loss. Same like sudden reduction, sudden construction. Yeah, sudden construction. It will have turbulence and it will have friction. So in real condition, we will have additional energy loss due to the turbulence. That's why you will need to take account the correction factor as well. Okay, this is the velocity at point 2, and then this is the flow rate. Flow rate is cubic meters per second. So you have to multiply the velocity by the orifice area. Yeah, the area of the small holes. This is AO. It means orifice area. Okay, any other question?
Sir, I have a question.
Yep.
Sorry if I'm gonna use bahasa Indonesia, but like I think you've said it in the past lecture. Is this yang kayak siram tanaman itu? Yeah. So if you like press it and then the velocity goes further, right? So I'm just wondering, in this orifice meter, does that apply?
Yeah. This is actually the same condition. When you pinch the hose, it means you reduce the area, right? So if you reduce the area, you will have increasing velocity. That's why the water can travel longer. But it's a bit counterintuitive, right? So if you feel like the water travels much longer, much faster, in your sense, the pressure will be increasing, right?
Yes, yeah, that's what I want to ask. Why is the pressure in 2 lower than in 1?
Yeah, because basically, what happening is it's increasing the velocity. It's increasing the velocity, but reducing the pressure. So the water will travel faster. Yeah, the water will travel faster, but basically the pressure is lower. Why actually the at that case, like this one, right? This is the pipe. Then you pinch the pipe. Yeah. So the water will goes like this with certain pressure, then will goes out, right? However, what happened? Even though at point 2 the pressure is increased, the pressure is decreased, yeah, compared to point 1, yeah, because U2 kan naik ya, U2-nya naik, P2-nya turun dibandingkan yang 1. However, at outlet you will have atmospheric pressure, right? Yeah. So
yes,
the
sir.
pressure, still there is a pressure difference between point 2, yeah, at the point when you pinch with the atmospheric. So basically the pressure that you feel, you encounter is the pressure difference between the point 2 and point at atmospheric. It's not between P1 and P2. Tetap lebih gede daripada tekanan udara luar kan ya, keluar dari selang itu. Makanya itu yang sebenarnya terjadi. Jadi kecepatannya itu naik, terus tidak serta-merta tekanannya juga ikut naik gitu ya. Yang terasa besar tekanannya itu karena beda tekanannya masih ada antara tekanan keluar selang dengan tekanan udara luar.
Oh, okay, sir. I get it. Yeah, okay.
Okay, yeah. Yeah, I know
Thank you,
it's
sir.
counterintuitive, but basically that's what will be happening based on the Bernoulli. So if you have increasing value of velocity, then you must have decreasing value of pressure, as long as the position of the pipe is horizontal. There is no change in potential energy. Ya, jadi selama pipanya itu lurus, horizontal ya, mendatar, berarti kan potensialnya tetap. Jadi tinggal tekanan dan kecepatan. Kalau yang satu naik, satunya harus turun gitu kan, karena totalnya harus sama. Ya, the total should be constant. So if the velocity is increased, then the pressure must decrease, and vice versa. Okay. Any other question? Okay. Then we go to the other types of flow measuring device. It's basically the same. When you want to measure the velocity here, yeah, the velocity or the flow rate, then this venturi is also reducing the diameter of the pipe. But it's not like orifice. The reduction is gradual. So it's same like reducer, yeah. So at point 2, it's still smaller than point 1, the area. The velocity will be higher, yeah, and the pressure will be lower. Same condition with the orifice. However, the schematic is similar with reducer. If orifice is like sudden contraction, is what is the name? I forgot. Yeah. So if the orifice is the sudden contraction, the venturi is reducer. Yeah, you can imagine this device is like that. If you just use the ideal approach using the Bernoulli, exactly the same. Yeah, the final equation exactly the same. The correlation between pressure and velocity is exactly the same. Yeah. But in real condition, of course, orifice and venturi will have different amount of energy loss. Ya, sama seperti yang tadi. That's why you need to incorporate the correction factor. But please try to derive all the equation. Try to derive the correlation between velocity at the small diameters, because it will have bigger and small diameters, like, and then try to correlate with the pressure difference between the inlet and outlet, because the inlet will be higher, right? So P1 minus P2. Try to correlate whether you can have this equation or not. All the equations should be the same if you are using the Bernoulli principle, the ideal principle. Just the correction factor will be different. Okay, yeah. Then if so, this one is flow rate. Flow rate is again meter per second. So if you want to convert to cubic meter per second, then you have to multiply by the area of 0.2, because the flow rate is the velocity is the velocity at 0.2. So the flow rate is also flow rate at 0.2. If you want to convert, this is cubic meters per second. If you want to convert into kilogram per second, what do you need to do? So you want to convert it into mass flow rate. Tadi kalau dari kecepatan ke volumetric flow rate dikalikan luas penampang, dapat volumetric flow rate, meter kubik per second. Kalau mau di-convert jadi laju alir massa, kilogram per second, dikalikan apa? From volumetric flow rate into mass flow rate, atau mass flow rate, apa, Ali? Anyone can guess based on the unit?
Density, sir?
Yes, you have to multiply it by density, because this is one, right? This is kilogram per second. So you have to multiply by kilogram per cubic meters. This is density. Again, don't get confused with the equation. You have to multiply it by the density. Yeah, you have density factor in this equation. Again, try to derive. Don't just believe what has been written in this slide. Yeah, but I want to show you. So this is the area. Yeah, this is the area. This is the correction factor, and you have the expansion factor. So expansion factor is basically it is another correction factor, but due to the turbulence that I have mentioned before. Turbulence has been created by the change of the diameters, right? Yeah. So the ratio between the smaller and bigger diameters will influence the turbulence. Yeah. The smaller the smaller the small diameters, yeah, it will create more turbulence. Ya, makin kecil si diameter kecilnya itu kan berarti Anda bisa bayangkan turbulensinya akan semakin besar. Dan orifice will have more turbulence than venturi. Okay, so in this graph, basically you can get the Y factor, the expansion factor, by knowing the diameter ratio, yeah, the smaller divided by the bigger diameters, yeah. This is for venturi, and the bigger this one is for orifice. Then you have you can calculate the Y factor by calculating first the pressure ratio. The pressure ratio is the ratio between the outlet and inlet pressure. Yeah, please pay attention. For the y-axis, it is increasing, right? So the maximum value will be 1. But for x-axis, it is decreasing. So it means if you have a lower pressure at the outlet, so it goes to the right. Ya, perhatikan angkanya ya. Ini ke atas makin besar, tapi ke kanan makin kecil. Then after you calculate the pressure ratio, you just choose based on your orifice or venturi, how much is the diameter ratio. Then after you can get the diameter ratio, you can get the expansion factor, then you can use in this calculation. How to get the pressure ratio? How to get the pressure ratio means you have to know the pressure at point 2 and pressure at point 1. Okay, then how to get the pressure at point 1 and point 2? By using the manometer fluid calculation, yeah, the rho GH one. Okay, any question?
Sir, I would like to ask.
Yes.
I'm just curious, to be honest. When do you use a venturi meter and when do you use orifice meter? Because they look pretty similar to me. Why do we have these two different shapes? Like what in what application do we use them? Because I'm pretty sure they should be different, right?
Okay. Yeah. Basically, you can either of them. Yeah. And in real application, both of them are being used. Maybe the preference, yeah, it can be comes from the how which one is easier. Like, is it easier to install a small plate inside the pipe, or is it easier to like connect, because it is takes longer, right? If you want to use the orifice, then you have to install the orifice inside the pipe. But if you want to install the venturi, it means you just can connect the pipe at one end and the other pipe at the other end. Yeah. So it depends on the real application. Dua-duanya dipakai. Both are being used to measure the velocity. The principle is the same. So you have more option basically. Which one do you want to use? Maybe if the arrangement of the pipe is not that complex, it's easy to install, to open the pipe, to put the orifice inside and then close the pipe again. Maybe you want to install the orifice, because orifice can create higher pressure drop compared to the venturi. But if it's not easy, then you can install venturi between pipeline.
Okay, sir. Thank you. That answers my question.
Okay, but both are easy to install. Basically, you just for orifice, you can provide like segment of the pipe, right, that already have orifice inside. Then you can connect this one with the other pipe and this one with the pipe. This one is also, you can provide like one segment of the venturi and then just connect with the pipe. I don't know which one is. I think venturi is more expensive compared to the orifice. I think, yeah, based on the construction. Okay, any other question? Okay, I think for the last part, this is rotameter. It is just for, have you seen this kind of equipment? Pernah lihat nggak alat seperti ini? Have you ever seen somewhere at your high school? Maybe? No?
No, sir.
Not yet, sir.
Okay. Basically, this is another type of flow meters. We call it rotameters, yeah, or flow rotameters. It's generally used to calculate, to measure the gas flow rate, either from the cylinder or maybe from other source of the gas. Yeah. So the gas is flowing from the bottom part, goes up. So while it's flowing, it will leave the how to call it, peluru. What is the stuff inside these rotameters? It will flows up and it will remain constant, static at certain position, and you can read by the number what will be the flow rate. Okay, how to get these things done is basically using the principle of buoyancy. Yeah, like flow, gas will be flowing, and then the balls or the peluru is flows upward, but then you will have pressure from the gas, right? Pressure from the gas from the top part, yeah, and then buoyancy force is also applied, so the balls can remain static at certain point. If you increase the flow, then the balls will goes up, but again it will remain static at certain point. So this is the application of not Bernoulli, the buoyancy principle. How to get the value? How to get the value means you need to calibrate. Yeah, you need to calibrate between the gas flow rate and the height of the balls. But since it will be influenced by buoyancy, so the density of the fluid is also important. The density of the gas is also important. So if it is calibrated, you already familiar with terms calibration, right? Paham ya yang maksudnya kalibrasi? Atau baru dengar? What is calibration? In simple sentence. Yasmin? Are you there?
Yes, sir.
Yeah. You already familiar with terms calibration? Or it is the first time you heard?
I've heard of it before, sir.
Sorry?
I think it's like to, I don't know how to explain it in simple terms, but it's like to make sure that like the measurement is correct.
Yeah, it's a process that we need to do to make sure that the value that shown by the measurement device representing the correct value. Yeah, so how to do it? You have to compare it with other system, yeah, which you can make sure it can provide the correct value. Like for the gas flow rate, you can use what we call wet test meter. Yeah, wet test meter is the equipment that you need to use to calibrate flow rate of the gas. I think later in MPA, metode pengukuran analysis, we will learn how to do the calibration. But what I want to point out is if you have these rotameters, you want to use it to measure the flow rate of, for example, oxygen or nitrogen, perhaps, yeah. Then you have to calibrate it with nitrogen as well. Yeah, so you have to use the same gas to calibrate the rotameters. Don't use other types. Maybe you're using hydrogen because the hydrogen will have different density than nitrogen. So the calibration value will not be correct. Yeah, later I think you will learn this in the practice. Okay, to maybe to end our class today, please do this exercise. This is the Venturi, yeah, arrangement of the Venturi, but different from the Venturi that I have explained before. The arrangement is vertical. Previously, it's horizontal, right? So oil, yeah, oil flowing, oil, the density is, specific gravity is 0.9, is flowing upwards, yeah, through the Venturi. And then there will be, there is some smaller diameter here, yeah. It means it will change the velocity and it will change the pressure. The pressure is represented in the manometer. So the manometer, because the pressure at point 1 is higher than pressure at point 2. So the height is like this. The left leg is higher because it's pressurized this part and then goes up like this. Okay. The manometers is using mercury with the specific gravity is 13.6, and then the height difference is 20 centimeters. The height difference between point 1 and point 2 is also 20 centimeters. So it's not like the horizontal one. The horizontal one, there is no height difference. in terms of the Venturi. Just heat difference in terms of the manometers. But in this case, you will have heat difference in the manometers and heat difference in the Venturi. So please be careful when you derive the Bernoulli equation. Okay, please try to do it at home, and then we can discuss it later and in our next class. Okay, thank you so much. And we will discuss this next week. Okay, thank you. Good afternoon.
Thank you.
Thank you, sir.
Thank you, sir.
Yes,
Thank you,
sir.
sir.